Hi students, this is Professor Gina and I'm making a video with some example problems from section 7.1. We're looking at simplifying trig identities and different formulas that we have. When you get into calculus, you will need to be able to transfer back and forth between different trig functions to simplify things that you're trying to take derivatives of or integrate. So I'm just going to go through a handful of examples. For this first example, it's a multiplication problem. And we're looking at the sine of x plus the cosine of x multiplied by the secant of x plus the cosecant of x. In all of these examples, we're following standard algebra rules that we would have if the variables were just more simple, like x and y. So we're going to just treat each of these the same way that we would. We've got a binomial multiplied by a binomial, and so we'll use a repeated distributive or a FOIL method. So I'm going to multiply sine of x times secant and then by cosecant. So I'll have sine x times secant of x, and then sine of x times cosecant of x. And similarly, I'll repeat with cosine, multiplying it by both of these items. So we'll have cosine x times secant of x, and then cosine of x times cosecant of x. Okay. So then what I'm going to do is kind of simplify each of these products individually. And one of the tricks that's often helpful is to change everything to be in terms of sine and cosine. So I'm going to switch secant of x to be 1 over the cosine. And then we know that sine and cosecant are reciprocals of one another. So this should just be 1, right? If I think about sine of x being multiplied by 1 over the sine of x, this is just going to end up being 1 here. Similar to for cosine of x and 1 over the cosine of x, this is also going to end up just being 1 here. And then for this last one, we have cosine of x times 1 over the sine of x. Okay. So I've got sine x over cosine x. In the middle there, I've got plus 2. And then this part all the way over here is going down here. This is going to become cosine of x over sine of x. So sine over cosine is tangent. And cosine over sine is cotangent. So I think my final answer is 2 plus tangent of x plus cotangent of x. You could have just left it as it was there, but this is the answer that was in the back of the book, so I'm just trying to stay standard with that. All right, next example. Let's do 1 minus the sine of t multiplied by 1 plus the sine of t. I'll draw a line here just to show that this is a new problem here. Again, using a distributive property, we can multiply this out, but we also know that there's this formula. This is a difference of squares. When I have two items, one that's being added and one that's being subtracted, when we multiply this out, we get a squared plus ab minus ab, and then minus b squared. And so this middle term ends up going away. So this is just a squared, minus b squared. This is similar, this is in the format of a minus b multiplied by a plus b. Again, you could multiply each component out, but what will end up happening is the middle terms cancel each other, and we should end up with the first term squared minus the second term squared, which is just 1 minus the sine squared of t. That looks pretty simple, but we could actually go one step further and we could use a Pythagorean identity. If we think about sine squared theta plus cosine squared theta, that equals 1. If I subtract sine squared theta from both sides, I end up with cosine squared theta equals 1 minus sine squared theta. And so that matches what I had back in my problem over here, so I can actually make this even simpler to be cosine squared theta. That would be my answer. All right, I'm going to get a new page here. All right, for our next example, we are going to kind of go in the opposite direction now, and we're going to try to factor. The first examples we were doing were multiplying. Now we're actually going to be factoring. So I'm going to factor sine of x times the cosine of x plus the cosine squared of x. One of the most simple ways that we try to factor things is to look for a common factor among each of the terms, and each of these has a cosine within it. I can rewrite this as cosine x times cosine x, right? So I've got this common cosine of x in both of them that could come out to the front. And then I still have a sine x left in the first term, and then a cosine x in the second term. So this would be the factored version of the original that we had. For my next example, let's factor tangent squared theta minus cotangent squared theta. We just had an example a minute ago that we called the difference of squares, when we have a squared minus b squared. That factors into a plus b and a minus b. So a is going to be tangent, so I'm going to have this as tangent of theta, plus b is going to be cotangent theta. And then I'll repeat the same thing, but with a minus sign in the middle. Again, in this example, we're using a is equal to tangent of theta, and b is equal to cotangent of theta. And so that would be our factored version. All right, let's do one that's a little bit more complicated. Let's look at sine to the 4th power minus cosine to the 4th power. This looks like it's in the format of a to the 4th minus b to the 4th, right? But what I could do instead is say that that's a squared. minus b squared squared. So let's write this in parentheses or in brackets, like a squared minus b squared. So my two variables in this case are a squared and b squared. Or rewriting this, I have sine squared, and then that whole thing is squared, cosine squared, and then that whole thing is squared, right? So this is a minus b, a squared minus b squared. So I'll have sine squared x plus cosine squared x. I'm using my variables as this is one of the variables. This is like a, and this is like b. And then sine squared x minus cosine squared x. So I'm still using a difference of squares. It's just what the variable is more complex. And then if I think about the fact that this is just equal to 1, that's the Pythagorean identity, right? Then I'm just left with sine squared x minus cosine squared x. And that we can use the difference of squares again to get, I think we just did that, a problem like that just a minute ago. Sine x plus cosine x, and then sine x minus cosine of x. So I'm repeating that difference of squares one more time. So that's the simplified or the factored version. All right, one more example of factoring. Let's look at 4 sine squared y plus 8 sine y plus 4. I'm going to do a variable substitution. I'm going to let, just use m equal sine of y. We had some examples a while back when we were doing factoring where we said that if we've got something squared and then something to the first power and then a number, it's in the form of a quadratic. And that if we do a variable exchange, we have it equal the variable that's in the middle. So the structure of this is 4m squared plus 8m plus 4. If I were to factor this on its own, I would start by pulling a 4 out to the front. And then I could factor this into m plus 1, m plus 1, right? So then let's exchange back for the original variable that we had. Instead of putting m, we'll write sine of y. Or in shorthand notation, 4 times the sine of y plus 1, the quantity squared. And that would be our final answer, factored version. Okay, for my next examples, I'm going to be looking at things that are given to us that we're needing to simplify. So these will be, this first example is a fraction that we're being asked to simplify. 30 sine cubed of x times the cosine of x over 6 times the sine squared of x oops, that should be cosine. Cosine squared x times the sine of x. Okay, so that's our problem. I'm going to rearrange this and break it into smaller components. I'm going to put the 30 and the 6 together. I'll put the sines together. And then I'll put the cosines together. So for the first part, 30 over 6, that's just 5. That part's easy, right? I have 3 sine x's on the top and I have 1 on the bottom. So that'll simplify to be sine squared x left on the top. And then for the cosines, I have 1 cosine on the top, I have 2 on the bottom. So simplifying that, I'll be left with 1 cosine on the bottom. So this is one way that we could write it. This is an acceptable answer. But maybe a slightly different way would be 5 sine, sine of x over cosine of x. And then I have another sine of x hanging out over here, right? Which would be 5 sine over cosine is tangent times the tangent of x. And then that other sine is just hanging out there. So this is an alternative answer. Okay. For our next example, let's simplify cosecant of negative x over the cotangent of negative x. Whenever we have a negative angle that we're taking a trig function of, we want to consider those odd even functions. The only functions that are even are cosine and therefore secant because they're reciprocals. So both cosecant and cotangent are odd functions. That means when we take the cosecant of a negative number, we end up with the opposite of the cosecant of that number. So, and then similarly for cotangent, that would be negative cotangent of regular x. So those two negatives are going to cancel each other out, and we have a positive fraction overall. So this is cosecant of x over cotangent of x. I'm going to switch all of these to be in terms of sine and cosine. So in the numerator, I've got 1 over the sine of x, and then I've got cosine over the sine of x. This is called a complex fraction. I have a fraction in another fraction, right? I've got one fraction here. I've got another fraction here. And the strategy for simplifying is to multiply by the least common denominator among both of those fractions. In this case, they both have sine of x as a denominator. So I'm going to multiply by sine of x over sine of x. I have to multiply the top and the bottom of the fraction by the same thing. So in the big numerator there, I'm just going to have 1 left over. And then in the denominator, I'm going to have cosine of x left over. What's happening is that this and this cancel, this and this cancel. And 1 over cosine is the same as secant of x. And that's our answer. Let's do a couple examples that have square roots involved in them. So let's simplify 1 minus cosine beta over 1 plus cosine beta. And this is in the square root. One of the tricks that we use when we have something like this, that these look like conjugates. Conjugates are when the sign plus or minus in the middle is the opposite. So I'm going to multiply both of these items by the conjugate of the denominator, 1 minus cosine beta and 1 minus cosine beta. Because what ends up happening is it creates a difference of squares for us. If I look at the denominator, I have 1 plus cosine beta and 1 minus cosine beta. And so that'll simplify in the denominator to be 1 minus cosine squared beta. The numerator is the same thing repeated. So it's that whole quantity squared. Well, in the numerator, I can take the square root of that, right? Hang on a second. Let me pause for just a second. Okay, so I'm going to go back and change this problem slightly. The strategy that I'm showing you is good in when we have problems that there's not a square root. But what I realized is that I actually want to have the item that's squared down in the denominator, because I want to be able to take the square root of that, and I don't want to have any radicals in the denominator, because then you have to rationalize the denominator. So what I'm going to do is go back and instead change this to plus and this to plus. Let's see how this will switch this over here. In our denominator, we have 1 plus cosine beta squared. Yeah. And in the numerator, we're going to have the difference of squares, 1 minus cosine squared beta. Yes, this is going to work out better. All right. So I'm going to split up this square root now. 1 minus cosine squared beta square root here. And then in the bottom, 1 plus cosine beta squared. But like this, and I'm taking the square root of that. So in the denominator, the square and the square root will cancel each other. So I've just got 1 plus cosine of beta. That's good. And then here in the numerator, if I do a Pythagorean exchange, Pythagorean identity, this changes into sine squared of beta. So what I have is the square root of sine squared beta. And that's just sine of beta over 1 plus cosine beta. And that's our answer. We're able to get rid of that square root symbol. All right, one last example. Let's look at cosine squared x times the sine of x multiplied by the square root of sine x. We have a rule with square roots that if we have two items that are multiplied, we can split them up, we can separate them. We use this for simplifying square roots, right? But we can also use it in this case to bring two things that are multiplied together under the same radical. So I'll have cosine squared x times sine of x times sine of x, and the whole thing is underneath the same radical sign. This is cosine squared x times sine squared x. And then I'm going to go backwards now. I'm going to say, let's split this into two separate things, times sine squared x. And because they're both squared, when I take the square root, I'm back to the original function. So I just get cosine of x times the sine of x. And that's my solution. All right, that's it for the sample problems for section 7.1. And then I'm going to make problems for 7.2 and 7.3 next. Have a great day.